Hey, welcome everybody. So today we have the honor of having as our guest Professor Pettini from University of Cambridge, and he has done his PhD in astrophysics at the University College in London in 1978, where he was one of the first to investigate the interstellar medium of our galaxy at ultraviolet wavelength. And then, since then, he has worked at the Royal Greenwich Observatory, the Anglo-Australian Observatory, University of Western Australia, and then at the University of Cambridge, where he currently teaches physical cosmology and stellar structure and evolution. So his research focuses mainly on high redshift galaxies in intergalactic medium, and he's particularly interested in studying the chemical composition of gas in distant systems with a view to unraveling their origin and evolution. So today we will talk about near-pristine gas at high redshifts, a window on early nucleosynthesis. Let's welcome our guest.
Well, thank you all for coming, and thank you for inviting me to give this talk. It's always a pleasure to come to Heidelberg, and it comes off this warranted by the number of friends and colleagues that I have here, so I'll try and put that right in the future. So here's the title of my talk today, staring at me from this wonderful screen. I was wondering whether you might need 3D glasses to look at my talk to do without those. As the title says, what the general idea of this work is to try and find some pockets of gas at high redshift, say 1 to 3 billion years after the Big Bang, which have remained uncontaminated as much as possible by the products of stellar nucleosynthesis. And once we found them, to use the chemical composition to try and unravel some clues on the first stars forming the universe. Well, this is a topic in general that would be familiar to many of you, and until now has been pursued primarily with stellar studies, with stellar astrophysics. So it's fashionable to give labels to these things. So now people talk about galactic archaeology, by which they mean that we try and unravel the oldest fossils left in the Milky Way and nearby galaxies about the first episodes of star formation. I like this slide by Anna Frabel. Shows what happens with a small part of the optical spectrum of stars when you move from the abundance of iron that you have in the sun. This is on a log scale for those of you who don't work with chemical abundances. So here's the stellar spectrum on the top. You can see this thing there. But if you come to stars which have lower and lower proportion of iron, to less than 1,000 or so here, and this is less than 10 to the minus 5, you see how the spectrum, all the spectrum lines disappear, and you're left with hardly any traces of iron. Now, this abundance is relative to the sun on the log scale, as I've explained. In the sun, the abundance of iron on the log scale is minus 4.5. So when you combine these two numbers, in this star here, there is 1 atom of iron for every 10 billion atoms of hydrogen. So essentially almost pristine. And yet that 1 atom of iron for every 10 billion atoms of hydrogen has to come from somewhere. None of it was, no iron was made in the Big Bang. So where did it come from? And so that's a general picture that we have of this process. At some time, at very high redshifts, say redshift 20 or 15, the first mini-halos or dark matter collapse, and the very first population, very first metal-free stars formed in these condensations were referred to as population-free stars, and these presumably were all very massive, because none are left today. We haven't been able to find any metal-free star at all. And so these two were very massive. They presumably exploded very quickly as supernovae, and they enriched their surroundings with the first products of stellar nucleosynthesis, which were then incorporated in later generations of stars. And those are the ones that we find and we study in the hill of the Milky Way. So the approach that we've taken to this kind of general problem is to say, okay, if that's the case, would it be possible to find those first metals made in the first stars, not in the second generation, but in the gas that formed the second or third generations of stars? And these clouds of gas, in principle, if they're there, should be accessible to observations from Earth now, because if they happen to lie in front of very distant objects in the universe. So the technique that is used, and has been used for a number of years now, to study gas at high redshift is called quasar absorption lines, and it's illustrated by this little simulation put together by Andrew Ponson, when he was a student at Cambridge. He's now at UCL in London. So what this shows you is quasar, just a very bright source at high redshift. It doesn't have to be a quasar. In fact, you can use gamma ray bursts or even galaxies. And this is the intrinsic spectrum of the quasar. And now we see what happens to the quasar photons as they leave the quasar and come towards Earth. And you see for each of those condensations of gas in the intergalactic medium at high redshift, you will find some narrow absorption superimposed on the quasar spectrum. And that absorption will tell you something about the gas that happened to lie fortuitously between the quasar and ourselves. Now and again, superimposing these forest of lines, which I'll show you in more detail in a minute, there's one Lamin alpha line of hydrogen, which is much stronger than the rest. These lines are associated, at least at the present time, with galaxies. And those are the ones that we're interested in studying. So here's now a real one of those very strong lines. They're called damped Lamin alpha lines, and all the rest of the gas goes by the name of damped Lamin alpha systems. So this is a real spectrum, and you see here how easy it is to pick out a very strong, with these characteristic rings, strong absorber of neutral hydrogen with column densities of order 10 to the 20 atoms per square centimeter or more, how easy it is to pick them out from the rest of these much more tenuous and highly ionized gas that is more generally distributed in the intergalactic medium. For the purpose of what I'm going to talk about today, all that we need to know about these damped Lamin alpha systems, or DLAs for short, is that they are condensations, they are gas clouds of very high neutral gas density. And the important point, and why we focus on these, is that of all the different classes of absorption line systems of gas that you find in front of quasars, it is these DLAs that, for a number of reasons that I won't go into, I haven't got time to today, they're the ones which are the ideal parameters for us to measure accurately a number of physical properties of the gas, including the chemical composition. The main reason is that the gas is mostly neutral, and so you don't have to make any allowances for ion stages that you don't observe. What you get is what you see, essentially. A slight drawback of using these systems, and something that has been a bit of a spine, of a thorn in the side of quasar absorption line spectroscopies since these things were first identified some 30 years ago now, is it is still unclear what kind of galaxies, if you want to call them galaxies, these damped Lamin alpha systems are actually associated with. And I'll give you two examples in the next slide. So there was a paper last year by Celine Peru and her group, and the idea here is that in the center of this image here, where this star is where there is a quasar at a redshift of 2.92 Celsius, it says there. That quasar has been subtracted out from this image, not to confuse the picture. And when you look at the spectrum of that quasar, you see in its spectrum a damped Lamin alpha system at a redshift of 2.35, for one in front of the quasar. And so what Celine Peru and her collaborators did was to image this field with symphony at the wavelength of the H alpha line of hydrogen at the redshift of 2.3541. And indeed, after you subtract the quasar, you find a strong emitting galaxy close to the quasar. I think this line here, this says 1 arcsecond, so about 1 arcsecond away. And when you look at the properties on this Dumpelman alpha host galaxy, it's actually a pretty normal galaxy with that redshift. It has a star formation rate, for example, of 17 solar masses per year, and many of its other parameters are similar to those of galaxies you normally find at those redshifts. So here's an example of a host galaxy of the DLA, which, as far as you can tell, is kind of normal. As a counterexample, you might think that if you can image the host of this gas at high redshift, it should be much easier to do at a lower redshift. Well, that's not always the case. Here's a paper the year before by an American group. They used HST to image very deeply the field of this quasar, with this alpha number here, at an emission redshift of 0.456. This quasar, from its UV spectrum, shows a very clear, normal Dumpelman alpha system at a low redshift of 0.110, 104. So you think this would be a really easy galaxy to image, and basically there is nothing in this field that matches this redshift. Again, the quasar's been subtracted out. They thought some of these blobs might be the Dumpelman alpha galaxy, but they're not. They're all different redshifts. And this gas causes this absorption. If it is associated with the galaxy, the limit on the galaxy luminosity must be, the galaxy must be fainter than 100th of L star. So clearly, you can find a whole range of galaxies that can give you one of these Dumpelman alpha systems, one of these very hydrogen-rich absorbers in the way. And it would be nice to be able to match the two. We haven't got there yet, not by any means. But as far as measuring chemical abundance is, in a sense, that's a secondary question. For the questions we're going to look at today, we're going to gloss over this uncertainty about the nature of these DLAs and proceed. So, oh yes, one of the steps that I forgot is that, of course, it's always difficult to, as I said, it's been difficult to find direct counterparts, partly because there's always a very bright quasar in the way that makes it difficult to see maybe a faint galaxy close to it. You can address this question with simulations. So you can ask, for example, do the simulations that are so successful at producing galaxy formation, to track the formation of galaxies over a possible time, can they tell us whether the Milky Way, for example, was a Dumpelman alpha system, let's say redshift 3? And this is what this simulation by Andrew Ponson here shows. This is a galaxy which by redshift 0 becomes something like the Milky Way. And in this simulation, we've got a color coding which corresponds to the color density of neutral hydrogen. Everything that's red, the dark red, is a DLA. And this is just turning it round, and a scale will come up pretty soon. There's 50 kiloparsecs. And so the answer to the question is yes, the Milky Way was a damp system at redshift 3. Its properties, its extent, its properties are roughly right. But also look at all the satellites, which have much smaller cores, where also if there happened to be a quasar right behind that red dot, you would also produce a damp system. So the simulations at least give us some confirm what the data tell us, that a whole host of different galaxies can, or condensations can give rise to a damp system. Okay. We know a lot. We don't know what kind of galaxies are associated with in general, but we know a lot about their metal content. People in several groups have studied the metallicity of Dumpelman alpha systems. That's relatively easy to do. It was even done with 4-meter telescopes going back to the 1990s. And now there's several hundred DLAs which have a metallicity of some sort, usually silicon, measured. And this is a distribution of metallicities. And as you can see, if you say, what am I likely to measure if I look at a random DLA, the answer is about a 30th or so, amount 1.5 or so. So in general, DLAs are metal poor. But the ones that we're interested in for the work that we're going to talk about today is this most metal poor end of the distribution. We want to push this as far as possible to the lowest metallicity, but not anywhere near the low metallicities that have been reached with stars in the galactic halo. But remember that there are thousands of stars that we examine that way, and only hundreds of DLAs. So So there is no reason why, when the statistics improve with time, it should be pushed to even to -4, -5, like the stellar work has shown. But for the moment, we want to look at these VLAs and try and measure their chemical composition in detail. So basically, here's how the project that I'm going to describe works. We start off from low-resolution spectra, done from surveys like the Sloan Digital Sky Survey and its offsprings of various kinds. There are now more than 4,000 damper alpha systems known to exist from this low-resolution spectra. We identify the ones that we believe are candidates for being of low metallicity or the lowest metallicity, and we observe them with shell spectrographs on 8 to 10 meter telescopes, URES, IRES, Subaru. Anybody will give us time. The quasars are normally 17th to 19th magnitude, so it takes 1 night per VLA sightline to get to signal-to-noise ratio when we just start doing abundance work. And then you can measure the abundances, at least of this group of elements here, CNO group, iron, aluminium, silicon, sulfur. I'll show you how the steps work. So here's an example of the Sloan Digital Sky Survey spectrum of the quasar. The quasar is the redshift of 2.42. That's the whole spectrum here. And you can see even from the Sloan spectra that here's a VLA, here's a strong absorptive feature that stands out, short on that 11.5 emission. It's at a redshift of 2.337. Here it is blown up. And now if you look at the redshift of this Laminar line for the silicon, oxygen, carbon lines, and so on, you see nothing. You see nothing because the resolution of the Sloan and the signal-to-noise ratio is too low to pick up weak features. So these are the kind of candidates that we then go in and look at higher resolution as being the most poor. And that's how now the same quasar looks like when you observe it with URES or high res. So all those lines which were not showing up at all in the Sloan spectrum are actually there. You can see here the same lines that in the previous slide were missing. But look how narrow they are. This is now a velocity scale that goes from -50 to +50. See, this gas has an internal velocity dispersion of only a few kilometers per second. And we think that there is some sort of mass metallicity relation, or even for VLAs, whereby the most metal poor gas also is associated with the lowest masses. And so these narrow, low velocity dispersion, weak absorption line systems are the ones that have the lowest metallicities, and the ones that we're interested in following up. These 3 steps that I have outlined are exactly the same one as many of you here are used to following when you look for the most metal poor stars in the halo of the Milky Way. You also start from large-scale surveys to narrow down some candidates that are particularly suitable for that look like they might be very low metallicity, and then you go in with high resolution and measure the balances. So it's exactly the same steps.
Max, sorry to interrupt.
I'm glad you did.
When you say low metallicity, you mean specifically iron abundance, or how loose is the term to be used in this context when you come to low metallicity?
In the context of DLAs?
Yeah.
Yeah. So, I'm trying to think of an intelligent way to answer the question. We take anything, but it turns out that in most cases, most elements are within a factor of a few of each other. So it doesn't matter very much which one you take. Let's say we take iron, for example. But these systems with 100 times more carbon than iron are not in our sample yet. There are some which are getting there. But basically, at this point, low metallicity means very low equivalent width metal absorption lines. And then we'll go in and measure the metallicities, okay, with different elements. Right, so these are the same steps that you're used to seeing followed for the stellar work. And in fact, the point of what I want to stress is that this work on the high redshift neutral hydrogen clouds is in fact highly complementary to the work that's being carried out with metal poor stars in the halo Milky Way, or its companions. Each method has a strength and its weaknesses, and when you put the two together, it can really help to complement each other very effectively. And much of my talk today will be to emphasize this complementarity. So let's look at potential problems that affect stellar abundance measurements and VLA abundance measurements, which essentially measure the composition of the interstellar medium in these distant constellations of gas and distant galaxies. When you measure stellar abundances, in many cases, you have to worry whether those lines are formed in LTE, local thermodynamic equilibrium, or not. The interstellar medium is a much simpler physical environment, and you don't have to worry, you don't have such worries. And similarly, you don't have to worry about the 3D structure of the gas. These are really, there are not concerns when you're looking at diffuse interstellar gas as opposed to stellar atmosphere. And of course, there's also the fact that most of the local work that we term galactic archaeology, until now is referred to the Milky Way halo, and now is being extended to the nearby companion galaxies. Here we have the option to probe lots of different galaxies at different redshifts, different epochs in the past. So those are all things that are pluses for the VLA work and potential problems for the stellar work. On the other hand, interstellar gas absorption lines saturate very readily, and that's not so much of a problem for stellar work, where you have a much larger array of spectral features that you can use. And so the dynamic range of the VLA abundance measurements is more limited compared to the stellar work. By dynamic range, I mean you have to get the right combination of gas column density and metallicity to be able to be confident that you can measure the abundances correctly. And also, in stars, you don't worry about dust depletions. Some heavy elements could be in the form of solids, like dust, which doesn't absorb light in the same way with medium absorption lines. And this has generally been a concern for interstellar absorption measurements, although at the low metallicities that we're interested in, this problem seems to largely go away. Okay, so with that introduction, what I'm going to do now is to show you some of the results that we have obtained in the last couple of years on the first survey for the most metal-poor natural alpha systems.
May I ask a question?
Yeah,
I'm using ionization corrections here. When you say most of the hydrogen is neutral, that doesn't mean that the sodium is neutral.
So this is the advantage of using damp systems. Basically, this has been known for a long time from the first Copernicus results in the 1970s, now confirmed, with sort of photonization simulations. If the hydrogen is neutral, then all the elements of interest here will pile up in the ionization stage, whose ionization potential is higher than that of hydrogen. Because essentially the clouds are self-shielded. There are no photons with wavelengths less than 112 angstroms, or energy is less than 13.6 electron volts. So I'm not saying that all the elements are neutral. Carbon, for example, is carbon plus. Oxygen is neutral oxygen. Sulfur and silicon are extremely ionized. But the point is that there are not significant corrections for sulfur-3 or silicon-3 because there aren't the photons there to ionize the gas at that stage. And we can check this because within the UV range where we do this work, there are lines from carbon-3, silicon-3, carbon-4, silicon-4, and indeed they make essentially no correction to the abundances. And this is only valid for these damp systems. So I didn't have time to go into a lot of details, but basically if you plot distribution of column densities for whatever you find in front of a distant source, quasar or gamma ray burst, it spans 10 orders of magnitude, from 10 to the 12 to 10 to the 22. And as you can imagine, the highest column density systems are the rarest ones, otherwise the integral would not converge. And so the very rarest, the highest column density systems are the only ones for which this is true. All the rest, you have to there's no self-shielding, and you have to worry about ionization corrections. That's why we pick these guys.
Can I also ask a question?
Yeah.
Maybe I didn't understand it well, but I'm a bit confused why you seem to say that for the stellar gas, it is LTE versus non-LTE is in favor of its reading.
There is no problem. Everything is in the ground state.
Okay.
All the lines we see are resonance lines from the ground state, and the reason is that the density of photons and particles is so low that there is nothing up in higher levels, unlike the solar atmosphere. And similarly, it doesn't matter if it's a sphere or a cube or any funny shape, so long as you're measuring a total column of gas to a sideline, and the geometry is irrelevant at the point. So these are all advantages compared to solar atmosphere. We don't have to worry about this. Please don't ask me if you can ask a question. Just ask me. It's really good. Yeah.
Okay, then I have another one. Do we, for these high current density systems, worry about optical thickness effects?
Well, so this is this third point when I talk about line saturation. If the lines, the absorption lines get too close to zero, then you get into the optically thick regime. And then you can't measure bandwidth anymore. So this is a concern. That's why this work has to be done with high resolution spectrographs as opposed to low resolution systems, because you have to be able to resolve the intrinsic shape of the line. And to our advantage, what's happening here is that we have a range of transitions for many elements of different transition probabilities for different F values. So if one line is saturated, often there is another one that isn't. It's not true for all elements. Carbon is a notoriously difficult one. But to our advantage, again, we're looking at low metallicities, and therefore this problem is mitigated. So if you wanted to ask me what the balance of carbon in DLAs was for the typical DLA, with a metallicity of 1/10 of solar or 1/30 of solar, I couldn't tell you, because for that metallicity, all DLAs with that saturated carbon lines. You can't measure that. Okay, so I'm going to talk primarily about the results on the CNO group of elements, and again emphasizes the complementarity with the stellar work. And so here's an example, what has been termed the oxygen problem, and what this plot shows you is the abundance of oxygen over iron versus the metallicity as measured by iron, and this is in halo stars. And as many of you would know, when you go to stars which are less rich in iron than the sun, down to about 1/10 or so, that oxygen doesn't fall quite as fast. So at this point, you have about 2 to 3 times more oxygen than iron compared to the sun. And this has been a linchpin for almost all galactic chemical evolution models, and has been interpreted in terms of the different timescales for the release of oxygen and iron from different ranges of stellar masses into the solar system. So far, so good. Now, when people then were able, with 8-meter telescopes, to expand this work to lower metallicity stars, they found a bewildering range of results, because what's happening at lowest metallicity to this ratio seems to depend on which features you use to measure metallicity. This forbidden oxygen 1 line here seems to have the smallest problems with corrections for 3D and for non-LTE, but it then becomes vanishingly weak at the lowest metallicity, which is why people then resorted to the other spectral features, finding somewhat different results depending on which one you used. And in particular, if you use these molecular lines in UV, there were reports some years ago that this was an almost continuous trend, so by the time you got to 10 to the -3, 9, you have 10 times more oxygen than iron. And that potentially is very interesting, because essentially this ratio, you can interpret it in terms of the initial mass function of the star that created those elements. And so, depending on the mass of the supernova, of the supernova progenitor, you see there's a strong dependence on the oxygen to iron ratio on this mass. And if really, at the lowest metallicities in the Milky Way, oxygen was 10 times more abundant than iron, then it would imply that those elements were made by stars with masses more than 40 solar masses. So that's the sort of thing that would be very interesting to assess.
Why is that ratio not a function of the mass function? You have the I here. Is it not a combination of what the initial mass function was and what the age distributions of stars are that do the enriching?
Yes, of course. This is just to give an example of how it depends on the initial mass function. Yes, for a spike. But you
cannot invert. I mean, how easy is it to invert the problem? Because that's implicitly what in the end
you want to do. And as I'll show, it's not that easy. Yet. At least. So here, this is exactly an example where if you could measure the same ratio in the gas at high redshift, free from these complications, you might get the answer. And so here's now the same plot showing, again, halo stars with open symbols, and the filled color symbols are all damp alpha systems from the survey that we published in the last couple of years. And in the range between 10 to the minus 2 and 10 to the minus 3 of in iron over hydrogen, you see the stellar and DLA data agree very well with each other, provided the stellar abundances are measured from the weak forbidden oxygen lines as 6 to 300 angstroms. So the fact that the interstellar medium and the stellar data agree with each other, if you use that transition, is telling you that that's the one that's giving you the right answer, probably, compared to the others. To emphasize this a little more, so here's the distribution of this ratio in stars and BLAs over the same metallicity range, -2 to -3 in FURH, and as you can see, they're pretty indistinguishable, provided you measure the oxygen from this line. And so here's an example of how the combination of the two techniques has helped us sort out what's going on. Interestingly, there's actually when you look at the errors, which of course vary from case to case, there's very little scattering in this ratio. So the average oxygen to iron is plus 0.35 on the log, and so that's an enhancement of a little more than a factor of 2 in both galactic stars and these high redshift VLAs down to metallicity of 1,000 for solar. It's not a big effect, and there's remarkably little scatter here. Unclear as yet what's happening at 10 to the minus, below 10 to the minus 3. We have very few points there, and it would be interesting to explore this range in future when more VLAs are discovered without those lowest metallicities. Again, for the reasons I just explained. If there is a turn up, an increase there, it would have important consequences for the stars that produce the very first metals. Okay, that was oxygen. Let's look at carbon. Carbon has a very complex behavior. What I'm plotting here now is carbon over oxygen versus oxygen over hydrogen. So a different measure of metallicity. And again, I've color-coded here. You see data mostly for thin disk, thick disk, halo stars, and DLAs. And let me just take you through this plot. So what's happening is when we move down from solar metallicity is that there's a drop by about a factor of 3 to 4 in carbon to oxygen as oxygen drops by down to 1/10 or so. This has been known for a while, and people, there's at least 2 different explanations for this behavior. One possibility is that a lot of the carbon comes from Wolf-Rayet stars, which is not really appreciated universally. Wolf-Rayet stars have very strong winds, and we know the winds they become less strong at lower metallicity for well understood physical reasons. So Wolf-Rayet stars are lower metallicity with less carbon into the ISM compared to oxygen. And there's also a possibility that it's taken the galaxy this long to get to here before the AGB stars, the Ternary Planetary Nebulae, also produce additional carbon. Probably both things are at play. Now the interesting thing here is that as you then move to even lower metallicities, we found a behavior which was unexpected. This is some years ago now. Essentially, all galactic chemical evolution models that can reproduce this, and we're now going from left to right in this plot, but all the models that can reproduce this behavior here will predict that as you go to lower and lower metallicities, this thing should drop even more. And the work we did in 2004 now, with stellar data, seems to suggest that actually that was not the case, and the carbon to oxygen recovered again to near solar balances by the time you got to month 3. And this is work that I did with a student in Cambridge, Chris Ackerman, and the only way at the time we could reproduce this result was with its nucleosynthetic yields from metal-free stars and population-free stars. They gave you this additional carbon that was required to explain this strain. But again, if you look back at this paper, we hedged our bets very much in saying, well, we're not really sure whether this effect is real or not, because we worry about metallicity-dependent non-LTE correction in the same story. And that was the motivation for going to measure carbon at the lowest metallicities in DLAs, and indeed the DLAs confirm the behavior of the stellar data, which has been confirmed also by more recent work. So there seems to be a source of carbon at the lowest metallicities, which is either counting positive stars, or the good suggestion you can also do it with rotation, provided stars rotate faster and faster at lower and lower metallicities. It remains to be seen whether this second mechanism is viable. And then the third interesting thing that's come from this is that we found some examples, one or two, of what seems to be a carbon-enhanced damper alpha system. And by carbon-enhanced, I mean with a high value of carbon to iron. So let me show you why this is now really interesting. And the thing is that when we look at metal poor stars in the halo of the Milky Way, you do find this bimodal distribution. Here we've got 10 to the minus 2, 10 to the minus 3, 10 to the minus 4 in iron. And these stars, there's a group of stars here from this work, the Japanese group, that are enhanced by 2 orders of magnitude or more in carbon. This is their distribution, their numbers as a function of iron, and they fall generally into 2 groups. So one group is also highly enhanced in the products of neutral capture elements, and they often exhibit radial velocity variations. And the idea then is that what you're seeing here is material dumped onto the star you observe now from a binary companion which has now disappeared when led through its evolution. And so that carbon has come from a companion star, and it doesn't tell you much about the gas from which the stars formed. Now, there's another group, there's ones there in red, which instead don't have any enhancement in the neutral capture elements. And their numbers, proportional numbers, increase as you go to the lowest of low metallicities. And so here, you have a possibility that these stars, these no stars as they're called, are actually reflecting the initial composition of the gas from which they formed. And again, that would have implication for the very first generation of stars that seeded these materials. And the fact that we found now an example not in a star but in a diffuse gas cloud at high redshift, 1 or 2 examples so far, will lend support to this idea that we're looking at the initial composition of the gas from which these stars formed. So this is an intrinsic rather than a later addition. I won't talk about nitrogen. Yes, just to tell you that, again, comparing with now H2 regions in nearby universe, the DLAs give us clues about the relative proportions of nitrogen and oxygen in a regime that is not probed very well either by stars or by ionized gas. We can talk about this after if anybody's interested in nitrogen. I want to just finish off, well, I'll not finish off, but I want to really stress one other aspect of this work which I find particularly interesting. So, to recap, on the slide, I forgot. So this is answering Ansal's question before. So if the idea here is to use these chemical clues to find out something about the initial sort of relations that may have produced these metals, how are we doing? So here's an example. So what I'm showing here is the typical chemical pattern in black of alpha systems that use metallicities. And I'm showing these two examples in these two quasars where we found some amount of carbon enhancement by 1 order of magnitude or a bit less. And the thing is, can you reproduce this pattern with nucleosynthesis by metal-free stars, by hot-free stars? And the answer is yes, you can. There's a whole library of models that you can
imagine by a single metal-free star or an ensemble.
An ensemble. It turns out you don't need very many. So for the first one that we published, you could do it with 10. And so this reference up there is this whole suite of calculations of nucleosynthesis by metal-free stars, where you specify a few parameters, the mass of the progenitor, or rather the mass range of the progenitor, and the explosion energy, and out comes the pattern of these elements. And in both of the cases that we found, we can indeed find models with these parameters, these progenitor masses, or rather, at least the peak of the distribution of Gaussian masses about those central masses, and explosion energy of these numbers that reproduce this elemental pattern that we see. But there's a lot of parameters in these models, a lot of knobs to turn, switches to flick, and so this doesn't, it doesn't elicit the consistency argument here, but we're still a long way from being able to do what we'd really like to do, which is invert the pattern and zoom in on some of the properties. But it certainly does in this game. Okay, so let's now just recap what we've done. What I've been talking about is using pockets of gas at around here, redshifts 2 to 4, for practical reasons. It's easiest to observe the DLAs there. I zoom in on the DLAs which are least metal enriched with these redshifts to find out something that happened here when the first stars reionized the universe. But this very metal poor gas that has remained hardly enriched up to these redshifts can also tell you something about what happened right here a few minutes after the Big Bang. And that would be the final topic of today. And as many of you might know, in the first few minutes of the life of the universe, the whole universe acted at temperatures sufficiently high for nuclear reactions to take place and fuse neutrons and protons to form deuterium, helium, and the other light elements. So it is well understood nuclear reactions. This Big Bang nucleosynthesis scenario is well understood and leads to rather precise predictions for the relative abundances of the light elements made in the first few minutes of a universe life. And it's usual to plot to the abundances of helium, which for historical reasons is given as Yp by mass, and deuterium, helium-3, and helium-7 by number, plot them as a function of the parameter eta10, which is the ratio of photons to baryons in the universe, in the units of 10 to the 10, and that in turn is related via the Hubble constant to the fraction of the critical density contributed by baryons. And so it's no exaggeration to say that if you can measure the abundances of these elements very precisely, you can weigh the universal baryons. I think, from what I've said so far, I hope you can then appreciate that these most metal poor damp alpha systems are the ideal physical environments where to measure the primordial abundance of deuterium at high redshift. And I'm going to focus on deuterium. One could have a whole conference, of course, on Big Bang nucleosynthesis with lots of different talks. We will not talk about lithium or helium today. I'll just focus on deuterium, which has a rather steep dependence on the baryons. And the advantages of using these metal poor DLAs are fairly obvious. So deuterium only gets destroyed whenever you turn gas into stars. That's a very simple evolution with stellar nucleosynthesis, like helium, for example, which is made of stars. And so the fact that we're looking at the lowest metallicities implies that we're very close to the primordial abundance of deuterium. There's been very little consumption of it through stellar star formation. Here's a plot from this work by Francis and Ishimaro that shows you the ratio of deuterium to the primordial value is a function of metallicity. And you believe so long as you are at metallicities lower than 10 to the minus 1, at 1 Tesla solar, then you're basically measuring the primordial value of deuterium. The deuterium absorption lines, well, deuterium is hydrogen, just with the extra neutron. So you find exactly the same lines in the Lyman series of hydrogen. Deuterium, because of that extra neutron in the nucleus, the electronic energy levels are shifted a little bit higher up. And this isotopic shift corresponds to a velocity difference of minus 82 kilometers per second. And that's pretty large as far as isotope shifts go, but still it's only a rather small gap in wavelengths. And so you need only the narrowest DLAs, the narrowest absorption systems to be able to see it all. So here's an example of the sixth line. I'll show you more in the Lyman series. Here's hydrogen, and here's deuterium, completely separated in one of these very metal poor DLAs. And other advantages are that with such high neutral hydrogen atomic densities, then with that we have absorption from many deuterium lines in the Lyman series. And so here's an example. Here's one of the metal poor DLAs we have observed at a redshift of 3.0. It has an ion abundance of 1/200 per solar. Here's the damp Lyman alpha line. There you see very clear. You can measure the chrome density neutral hydrogen very, very accurately. And now here are all the Lyman series lines from Lyman alpha to Lyman 14, from the ground state down to the first excited level up to the 14th excited level. And as you go up and up the Lyman series, you begin to resolve quite clearly the absorption lines of deuterium that go with hydrogen. This is about the best measure we found, the best case we found for measuring the abundance of deuterium. So we developed a specific spectral analysis method that was focusing on just determining the deuterium to hydrogen ratio from the data. And without, I haven't got time to go into great details here, but this emphasis was Monte Carlo simulations to understand, as well as we could, the random and systematic errors that were affecting our results. And you see, look at the scale here, these are pretty small ranges in the value of deuterium to hydrogen. And we can also see how this value depends on various parameters that go into the model. And let's not so worry about that. Let's cut to the chase and give you the answer. So, people have been aware that you could do this since the 1970s. They had to wait until the era of 8 to 10 meter telescopes to be able to do it. And even then, amongst all those 4,000 DLAs known, only a few have all the right combination of parameters to measure the primordial abundance of deuterium reliably. So, after 20 years of high resolution spectroscopy, we have a prime sample of about 10 such measurements of the primordial abundance of deuterium prior to the one that I'm going to show you now. And so that's the latest one that we were able to do, according to our estimate, more accurately than ever before. Got the primordial abundance of deuterium down to 2%. And this translates also to a pretty accurate value for, that's random and systematic, and that translates to a pretty accurate value of the omega baryons from big bang nucleosynthesis if you just use this one measurement now. Notice that the error is actually doubled in going from deuterium to omega baryons, and it's doubled because actually one of the nuclear reactions this capsule of a proton by deuterium to form helium-3, has a rather uncertain nuclear reaction rate. I like to show this because it's telling, what it's saying is we've got more precision in astrophysical measurements than the lab measurements of some nuclear reaction rates. And that makes me feel pretty good. Well, somebody would say, like Hans Walter, well, why bother doing this? We can do it from a cosmic array background anyway.
Thank you for creating.
And what he would mean by that is, for previous connections, the most recent results is Planck, of course, has given us this fantastic picture of the CMB sky, and this really accurate measurement of this power spectrum, these temperature fluctuations, and encoded in this are a host of cosmological parameters, including omega baryons. And I'll show you how that comes about. I'll show you from Who webpage what happens to the spectrum if you change omega baryons. Omega baryons is shown with this bar at the, on the side. Let's show it again. So omega baryons goes from 0.02 to 0.06, and as you increase it, you increase the contrast between the odd even number peaks in the spectrum in the temperature fluctuation power spectrum. And so with the latest CMB results from Planck, the 16th paper in the big batch that came out in March, April, they also record the measurement of the baryons from the CMB fluctuations, and that is 2.21 plus or minus 0.03 times 10 to the minus 2. So that's the CMB measurement. That's the deuterium measurement. Okay? Very close to measurement. And that's actually very interesting because if you go back to one of these plots, what we're saying is we're measuring the density of baryons from baryonic acoustic oscillations in the plasma here, when the CMB was emitted, and also by a completely different mechanism somewhere here. And any departure from the standard models of physics would make these two measurements disagree with one another. The fact that they agree so well with each other means that we can place limits on departures from the standard model. Sometimes these departures are coded in terms of, for example, the number of neutrino families. And so we can place a limit on the basis of this agreement on the number of neutrino families being 3.0 plus or minus 0.6. And that's simply kind of taking this distribution measurement for various of this unit. Okay, I'm practically done. Let's just go through a quick summary because you've been very patient. I would like you to take away from this talk that there is a population of neutral gas clouds, the high redshift, which have undergone minimal enrichment by solar nucleosynthesis. They're called the very metal poor Dampler alpha systems, and chemical studies of these systems can complement very, very effectively analogous measures in all the stars in the Milky Way and its companions. I talked about the results in the oxygen abundance, which shows that the features to use from stars is the forbidden line 60 angstroms. That's the one that agrees with the interstellar measurements most closely, and it seems to imply only very modest alpha enhancement in the Milky Way and in these distant galaxies by only by the factor of just over 2. Unclear yet what's happening at the lowest metallicities. There appears to be a source of additional carbon at the lowest metallicities, which may well be to do with population of 3 stars, and that's supported by the discovery of some possible local analogues to the carbon enhancement of 4 stars, as we know enhancement in neutral capture levels. Deuterium, there's a concordance between omega baryons from CMB and deuterium measurements, which seems to imply little departure from the standard model of physics. And I'll just conclude by thanking all my people that are involved in this work. So Ryan Cook, with the lion's share, when he was a PhD student in Cambridge, and is now at the University of California at Santa Cruz. Andrew Thompson, who's just taken up a position with UCL in London. Gwen Rudy at Caltech, and Regina Jorgensen in Hawaii. Chuck Sadell, Michael Murphy, Paul Nissen, I couldn't find a picture of him, and thank you for listening.
Thank you very much for a very interesting talk. Are there any further questions? Yeah, please go.
Could you explain why the ratio of deuterium detectable, like deuterium DLAs, is such a small fraction of the overall metal core DLAs that you have?
Why we only have such few cases, only 10 cases? Is that what you're asking?
Yeah.
So the reason is that, without me getting the slide back up there, if you remember the distributional metallicities, there are only very few DLAs, 5% or so, which have a metallicity less than 10 to the minus 2 out of the whole sample. And those are the ones where you would have enough of a gap to see the isotope shift. But then the problem is, if you remember that sort of little cartoon movie at the beginning, when the photons are traveling to the intergalactic medium, there can be hydrogen and unconnected with the DLAs into other redshifts that can mess you up. There's a lot of foreground, basically there's a lot of foreground, what you call foreground confusion. And so you have to get everything right in the few cases where you can see the
Yeah, essentially a follow-up on that. Do you think it's possible, and have people tried to do a statistical analysis of the Lyman alpha forest to see if they could sort out the deuterium contribution there? I mean, for each individual line it's impossible, but if you do a filter or something.
Look, I couldn't agree more. We have a strong plant group in Cambridge, and they have to get rid of all this blinking galactic program before they look at the CMB, And so they develop all the tools to do that, and I've had many conversations with Coffee about applying the same techniques to the Lyman alpha forest. It would be really a very useful thing. They all agree it's a very good thing to do, but everyone's too busy with other things. So yes, it's something that is definitely worth thinking into in the future.
So you said in response to my question about inverting the problem, that you can't do it yet. What is it, aside from generic more data, is it more suitable systems or more precision on the elements on the systems you have?
Well, I think the precision is good enough, probably, for what we want to do. 0.1x, 0.05. Small systems to get a broader picture. We still only have a few. And they're done, most of them are at the 10 to the minus 2, 10 to the minus 2.5 level.
More systems, by now most bright quasars in the sky unknown. So does it mean more telescope time or bigger telescopes?
Bigger telescopes is the answer. And I don't know if I got time to show a couple of slides. So this
couple of slides, maybe.
No. I'll show you later. So the answer is bigger telescopes, I'm afraid. We've done pretty much what can be done at present in the north. It's with the surveys that will extend to the south will definitely help, but we're coming up against the limit.
You showed the surprising similarity of the abundance ratios coming from DLAs and extremely poor radio stars. There's a tendency to now move from the galaxy further out, looking at other local galaxies. But from this picture, would your prediction be that in the end, when we are able to study individual stars up to X megaparsecs, that we will see again the same thing everywhere?
That's an extremely good point. And I think in terms of the metallicity range between 10 to the minus 2 and 10 to the minus 3, I would say, for example, for oxygen to iron, yes, because we have 22 measures of that in the metallicity range about random sight lines in the universe at redshift 2 to 4. So, okay, small number of statistics is 20, not 200, but in terms of giving a DLA, it could be Milky Way type galaxy, or it could be the precursor of Fornax or Draco. So I wouldn't expect in the metallicity range a large scatter. Of course, there are many more stars that can be done in these galaxies with multi-object spectrographs, than you can do with DLAs, which are everywhere. So, but yeah, I think that is correct in what you just said. Now, the metallicity less 10⁻³ is very sparsely probed regime, so I think not that many predictions there.
Good for time. One short question.
It's a short question. I don't know about the short.
Sorry.
I was wondering, can you measure magnetic fields in these objects?
People that claim that you can.
Do you trust it, and what did you
Look, our Wolf published a paper a few years ago in which he reported that Zeeman splitting and a surprisingly high magnetic field of high redshifts. Because all our ideas, magnetic fields is that they go up with time, so it's surprising to find strong primordial fields.
It's not surprising. Quickly, this is mostly done.
Okay. So my answer is that there have been very few measurements. Is something that certainly can be received further. Yeah.
Okay, I would say let's thank you very much again. And